Good morning, good afternoon, and good evening. This is Ken Canavan, and I'm the Chief Technology Officer for Westinghouse. Today, we're here to talk about how exascale computing can be used to predict nuclear fuel performance. With me today will also be Antoine Claes, and Antoine will take the hard part of describing all the technical details. But from my perspective, what I'd like to talk to you about is nuclear fuel represents the first barrier to fission product release and therefore is a very important aspect of nuclear safety. When we go to introduce a new fuel assembly or pellet or rod into the reactor, it takes quite a bit of testing and quite a bit of preparation. Antoine's going to talk about that a little bit further and in more detail, and specifically about what we've come to call lovingly cook and look. And cook and look is expensive and it's time consuming. And exascale computing can allow us to simulate most of that work. Antoine, to you.
Thank you, Ken. As you can see on the illustration, the designing, building, qualifying, testing, and licensing can take many years. This is because we need to get a lot of data, and this is a fully empirical process. We have no or little fundamental understanding of cause and effects. For this reason, the applicability range is the same as the validation range, and we need many experiments to span all the different parameters for the different thermomechanical models. To reduce the time between design and the final NRC approval, we can use experiments and modeling together to make a better choice and understand the material. The design can be improved since materials, doping options, and conditions in general can be tested, leading to a faster design phase. The mechanistic understanding acquired can also allow to understand experiments and correct experimental bias, for instance. This understanding can be used to argue that the applicability range should be larger than the validation range. Changes of behavior can also be predicted, leading to targeted experiments. As a result, we have fewer experiments with a larger value and an increased predictability for our models. Before talking about why we need exascale computing power, let's talk about why conventional modeling needs more and the current capabilities are not enough. Material modeling is a trade-off between precision and computational cost. A more precise model will require more time. In Westinghouse, the main framework is the density functional theory 1. It is used to start most of the lower length modeling. It is currently limited to a couple hundred atoms. This makes some modeling complicated. For instance, systematic studies of complicated simulations such as phonon spectra in doped materials are not doable. Large material defects such as dislocations, bubbles, and complex nucleation processes cannot be done using density functional theory, and some slow processes are also hard to assess, especially when modeled together with fast ones. To bridge the scales up to the engineering scale which is needed, we usually use several frameworks, and we use one to inform the other ones. Every time we change, we lose information, so we would like to avoid changing framework as much as possible. Access to exascale computing would allow to improve predictability of existing materials and design of new materials. As a summary, with the current capabilities, we can perform small simulations with very few defects. We have a hard time assessing temperature effects, and we cannot do systematic studies or are very limited in a number of elements. With exascale computing, we could assess large simulations with many defects. We could reach temperature effects and do systematic studies.
I just want to summarize by saying that the capability that exascale computing provides will enable us to move much more quickly through testing and qualifying new fuel, essentially reducing the time, reducing the cost, and increasing the safety of nuclear power in general. We look forward to this all, of course, being brought to you by the power of exascale computing. And I'd just like to wish you all a happy exascale day.